All right, so here's the continuation of section 10.4. So polar equations are going to produce some shapes that you've probably never seen before. So let's just talk about the names of some of these shapes that look kind of like little jelly beans or something. First up, we have this shape right here. It's called a cardioid. It is named as such because it kind of looks like a heart, right? Have you ever heard of like cardiac as referring to the heart? That's where this term comes from. Now, if this little cardioid's little tip right there is away from the origin, then it has a different name. It's called a dimpled limicon. So this little thing right here, you may notice that C has like a little tail on it. That's French, and it's a soft C. So it's not limicon, it's pronounced limicon. So it's what's called a dimpled limicon. This one, you could say that cardioid is a very specific type of limicon. So you'll notice I don't write that little thing on the C very often in English. We don't tend to write that little thing. But if you see it, I wanted you to know what that little thing meant. You could have a limicon that's going in this direction, kind of sideways, and it could be more than just dimpled. It could have a full-on inner loop, which cleverly is named a limicon with an inner loop. We could also have something that looks like a little infinity symbol. That's called a lemniscate. So yeah, this is going to be a lot of really unusual graphs that you're not used to seeing. We also have, the lemniscate has like 2 petals to the rose. We also could have like a 3-petal rose looking like a little prop on a plane, or we could have a 4-petal rose. And you could have even higher petaled roses for those. Now, you don't have to memorize the equations that are going to go with each one of these graphs. I know the book kind of takes that approach of like, oh, if you see it's like A plus B cosine theta and A is greater than B, then it's going to be this. And no, we're not doing that. No. So here's what we're going to do. I'm going to give you a polar equation. We're going to test it for symmetry. We're going to sketch the graph. We're going to name the shape. Okay, we're going to use the calculator to sketch the graph. We're not going to actually plot points. That's too much work. So let's get started with 1 minus cosine theta. Let's start off and test it for symmetry. We know there's 3 types of possible symmetry that we can have. We can have symmetry about the polar axis, the line theta equals pi over 2, or the pole. For symmetry about the polar axis, we're going to replace theta with negative theta. So if I replace theta with negative theta in the original equation here, we know that the cosine is an even function. So cosine negative theta is the same as cosine theta. We get the exact same equation back. So yes, there is symmetry about the polar axis. If we want to talk about the symmetry about the line theta equals pi over 2, we have to replace r and theta with negative r and negative theta. So if I replace both of these, again, the cosine function's even, so cosine negative theta is the same as cosine theta. But now I've got this extra negative over here hanging out, so it's not the same. Now remember, that does not mean, you may be like, oh, so it doesn't have symmetry. No, it's inconclusive. It may or it may not have symmetry. The test is inconclusive. You don't know. The third type of symmetry is the symmetry about the pole or the origin. We're going to replace r with negative r. So if we do that, we get kind of the same situation we were in with the last one. It's not the same, so it's inconclusive. May or may not have symmetry about the pole. We know nothing. Now, let's graph it. I did go ahead and write out exactly how your calculator needs to be in order to graph this. You do need to be in polar mode. That means that you need to hit the mode button. Make sure you're in POL, polar mode, and radian mode for this. When you're in polar mode, your y equals is now your r equals screen. Your variable key, that xt theta n button, that changes based on the mode you're in. X is function mode, t is parametric mode, theta is polar, and n is sequential mode. Because we're in polar mode, we're going to have a theta for our variable. All right, so let's graph this. Oh, I didn't even write it down. Oops, just bumping stuff all over the place. What was what was it? Oh, it was 1 minus cosine theta. There we go. So 1 minus cosine, and then my variable key. Now, something to note with these graphs, that it's very important that all your settings are correct. And I'm going to show you what happens if these get all wackadoodle, okay? So under window, I've got my theta min at 0. My theta max is at 2 pi. So if you just want to hit 2 pi, it will automatically change it to a decimal. And I have my theta step at 0.1. I'm going to show you what that means. It's easier for me to show you than to try to tell you. Then I'm going to hit zoom forward. That's kind of a zoom in, almost like a 5 in each direction. So you can see that this looks like one of those little dimpled limicons, but because the tip is right there at the origin, that little bump right there is at the origin, it's a cardioid. We can tell from looking at the calculator that it's going to go through right here at 1 and down here at -1, and it's going to cross back here at -2. So that's about all that I want you to be able to sketch from this. Now, let's talk about that theta step. Let's go to the window again. This number right here, if it's too big, your calculator won't plot enough points, and that shape is going to look all kinds of wrong. All right, so let's say that I make it 3. It's going to be way too fast. See that? It just drew a line. It was like, okay, you want me to plot pretty much nothing? Okay, cool. Let me make it 1. Look at that. It didn't plot enough points to get a good idea of what the graph looks like. So, you know, if you go with, say, like 0.5, I mean, that's fast. It's still kind of, you know, lumpy and stuff, but 0.1, slow, smooth, okay. If you go too slow, if you were like 0.01, now we're plotting way too many points, and it's going to take all freaking day. You see what it's doing? Oh, Lord. If you just hit second on, so if you just turn it off, it will stop right where it's doing, you know, right in the middle of what it's doing. So if you do get it stuck somewhere like that, just turn it off. Just hit second on, and that's like an abrupt stop to it. Now, notice that this cardioid here, look at that symmetry about the polar axis. Remember, the polar axis is the x-axis. Look at that symmetry, just like we predicted it would be. So, beautiful, huh? Yeah, it is. All right, let's do another one. Let's go with 1 plus 2 sine theta. Let's start off with the symmetry again. Same 3 symmetries. Polar axis, theta equals pi over 2, and the pole. So the polar axis, we're going to replace theta with negative theta. The sine function is an odd function, so that means the sine of negative theta is negative sine theta. That is not the same as the original, so inconclusive. We know nothing about that symmetry. All right, so we'll try something different. Let's try theta equals pi over 2. We're going to have to replace r and theta with negative r negative theta. So if we do that, this is an odd function, so 2 sine negative theta pulls this negative out here. That negative, so close, right? If I divide through by that -1, so close. That 2 ends up positive, but now that 1 is changed. So it's not the same. So again, test is inconclusive. All right, how about the pole? Surely that one's going to be our winner, right? Yeah, no. So basically, we know nothing about the symmetry. We're not guaranteed that it has to be symmetric, and we're not guaranteed that any of these are going to work. So I don't want you to think that the first 2 failed, so this third one, this is it. This is my win. So we graph this. This is 1 plus 2 sine theta. So 1 plus 2 sine theta. Let's go to the graph using the same settings as before. A little slow here, probably because I forgot to change that step. Oh, look how painful it is, but look at how pretty it is. Look at that loop, like a little toilet seat cover. All right, so I'm going to go up that sucker right there to 0.1. And then, nice little limousin with an inner loop. And you can see those key points that are labeled here from the calculator, that's up here at 1, that's back here at -1, that intercept right there is 1, and then this one up here is 3, and yeah, I get that it's not really smooth, but what you gonna do? So it's called a limousin with an inner loop. Right. Let's do another one. So really the toughest part of these is going to be that symmetry. You know, everything else we're just going to use the calculator for, so it's not going to be too terrible at all. So let's test this for symmetry. We're going to replace theta with negative theta. The sine function is odd, so this negative is going to come out in front. That's not the same as the original, so the test is inconclusive. All right, let's change the r and theta. So if I put negative theta here, sine function's odd, so that negative is going to come out in front. But check it out. Those two negatives are going to divide off, and we get the same equation. So yes, we will have symmetry about the line theta equals pi over 2. Now remember that's like, kind of think of that as like the y-axis. And the pole, if we replace r with negative r, we get this, which is not the same, so the test is inconclusive. If we graph this, let's see, it was 4 times sine 2 theta. Ooh, what did I do wrong? Oh, I'll put an extra parenthesis. Ooh, picky patty. Okay, fine. Ooh, check it out. Got a little 4-petal rose going down here. So we get a little 4-petal rose. So the one thing I want you to do is just kind of sketch what it looks like and then give it a name. You can also see that the only symmetry we were guaranteed was that theta equals pi over 2 right here, but you can see it does actually have symmetry about the polar axis and about the pole. So it actually has all 3 symmetries. The tests were inconclusive for 2 of those 3. Okay, last one for this section. And this one's going to have an r squared going on in it. So for the polar axis symmetry test, we're going to replace theta with negative theta. The sine function is an odd function, so that negative is going to come out in front here. And that is not the same as the original function, so inconclusive test. If I replace r and theta, ooh, check it out. That r squared right here says that I got to square all of this. So that negative is going to square and become a positive. That negative, because sine's an odd function, is going to come out here, not the same. Inconclusive test. The pole, okay, let's replace r with negative r. Because this is squared, it's going to be r squared, so it is the same. So we get that there is definitely symmetry about the pole. Remember, that's like the origin. Now, how are we going to graph this with that r squared in there? Well, the calculator, if you hit the y equals button, has an r equals. So here's what we're going to have to do. We're going to have to just take the square root of it. And technically we need to do the plus or the minus, but I'm going to show you that really if you just do one of them, it'll be fine. So if I do the square root of 4 times the sine of 2 theta, get that lemniscate. If you wanted to graph the negative version of this, you would get the same thing. So you don't really have to worry about it, but we get that kind of 2-petal rose, or that little infinity sign, which is called the lemniscate. And notice that it does have that symmetry about the pole. It's not symmetric about the line theta equals pi over 2. It's not symmetric about the polar axis. So it does only have symmetry about the pole, which is exactly what we were expecting out of this. All right, so that finishes up section 10.4.